Hi all. Welcome to the 8th problem solving session of the course Spectroscopic Techniques for Pharmaceutical and Biopharmaceutical Industries. I am Clarice from IIC Bangalore. Today we'll be discussing a couple of problems from the fluorescence spectroscopy part. Yeah, it all starts with okay. There is quite some time between loading the slides and how I change it here. I hope it will be visible for you to see it soon. So yeah, it all starts with molecules that can fluoresce. So there are certain criteria that we have to follow to that we have to uh, yeah, there are certain criteria that a particular molecule to satisfy to fluoresce. So here we have been asked to find um, among these two pairs of the molecule which we would expect a greater fluorescence quantum yield. So yeah, we have been taught in class a certain criteria for a fluorescent molecule having a rigid structure, delocalized electrons, intense absorption band, things like that. So we have to use those bases to distinguish which molecule is going to fluoresce better than the other one. So if you look at phenolphthalein or if you look at phenolphthalein or fluorescein, both of them are molecules which give fluorescence, and we have been asked to find which will have a greater fluorescence quantum yield. Fluorescence quantum yield, fluorescence quantum yield Q Q is equal to number of photons emitted by number of photons absorbed, and this can also be written as can also denoted in terms of emissive rate of fluorophore and the non-radiative decay rates, where emissive rate is gamma. So Q is equal to gamma divided by gamma plus KNR, where NR denotes the non-radiative decay rate. So yeah, so if we ask if we have been asked in among these two molecule which one has a greater fluorescence quantum yield, it also if we have been asked about this particular uh, this particular question, we have to find out whether the molecule has a rigid structure, whether it has delocalized electron, which one has greater delocalization, things like that. So if you look at fluorescein can have better delocalization compared to fluorescein, but at the same time, if you look at this carbon, it is sort of like tend to rotate, right? It is more flexible compared to fluorescein. So if you look at the delocalized structure of fluorescein, we can have the we can have sort of better delocalization in this particular case. Here also we can see we don't have that much farther a delocalization of electrons in fluorescein compared to phenolphthalein. But the thing is, phenolphthalein is comparatively less rigid than fluorescein. In the sense, it has a carbon which is sort of like a um, yeah, which sort of like is not a part of ring, and it can adopt different orientations, because of which, yeah, if you look at this, it's going to be, sorry. And this delocalization can also happen towards this ring. So we have better delocalization here compared to fluorescein. Fluorescein is far much more rigid, but at the same time this is also rigid because of this double bond in one of the sides. If you look at one of the other bonds, it is sort of uh, slightly flexible, but yeah, so but because of better delocalization in case of phenolphthalein, it has better quantum yield compared to fluorescein. Uh, Here also we have been asked for a set of a pair of molecules which has the better fluorescence quantum yield. So here also we can think of how the delocalization happens, and how it is going to affect the uh, affect the uh, affect the rigidity of the molecule and things like that. So if you look at this particular molecule, this has a double bond character here, which makes it rigid compared to this one, because this is just a single bond, so it is more flexible. And here um, here also we can sort of have a double bond character by donation of this lone pair in nitrogen to the uh, yeah, to the single bond between N and between this nitrogen and this nitrogen, which leads to a this sort of a bond. And yeah, so we'll get give rise to a this sort of a um, zwitterionic complex, which can also sort of give a double bond character to that particular bond. But compared to this one, this is more flexible. So rigid molecules has better quantum yield. So we should say that this one will have a better quantum yield. Yeah. Now, this is just about this is not a question per se. It's about what are the different time scale of the processes that are involved in the molecular absorption and the fluorescence. So this is a Jablonski diagram which has been covered in the class. So the ones shown in blue are absorption process. So this corresponds to the S0 state, which is the ground state, and S1 is the singlet ground state, S1 is the singlet first excited state, S2 is the singlet second excited state. Any excitation of electron from the singlet ground state to any of the singlet excited states is being upon any irradiation by a um, electromagnetic radiation is called absorption. And it can go from the lowest vibrational level of S0 state to any of the uh, vibrational states of singlet excited states. So that's what is shown if you look at the first arrow here. Yeah, okay. If you look at the first arrow here, it is going to the 1 0 1 2 3 4. We are going to the fourth excited state of excited state of vibrational level in second singlet excited state. So yeah, likewise you can see that excitation happens to any of the vibrational energy level in one of the excited state. And the time scale of absorption processes are in the is in 10 to the power minus 15 seconds, and it immediately it can undergo various radiative and non-radiative relaxation pathways. So one of the relaxation pathways are internal conversion or vibrational relaxation. So internal conversion is the transfer of electron from one of the higher order singlet excited state, which is S2 here, to one of the excited state of one of the vibrational excited state of, or any of the vibrational states in singlet first excited state of singlets. And that is called internal conversion. Vibrational relaxation is the relaxation of electron from higher vibrational energy level to lower vibrational energy level. Here this arrow denotes the relaxation of electron uh, from fifth excited state to fourth excited state of first of S1 electronic state. And yeah, so internal conversion where molecules comes from higher excited state to higher excited state of higher electronic excited state to lower electronic excited state, which is called internal conversion, is in the range of 10 to the power minus 14 to 10 to the power minus 11 seconds. And vibrational relaxation where the molecule come from higher vibrational energy level to lower vibrational energy level is in the order of 10 to the power minus 12 to 10 to the power minus 10 seconds. Fluorescence happens when the electron comes from the lowest vibrational energy level from the first excited state, singlet excited state, to the any of the vibrational energy level in singlet ground state. So which is denoted by different green arrows. You can see that the molecule, sorry, we can see that the molecule, yeah, you can see that the molecule coming from higher yeah, I'm just tracing over this green arrows. So it's coming from the higher lowest in a vibrational energy level of the first excited state to the ground state of any of the vibrational level in the ground state. And This happens over a time scale of 10 to the power minus 9 to 10 to the power minus 6 seconds. At times, the molecule in the electrons in the molecule which is in its lowest vibrational energy level of first excited state can go to triplet states by a process called intersystem crossing, which is denoted by another blue arrow, and it is in the time scale of 10 to the power minus 11 to 10 to the power minus 6 seconds. Yeah. And once it comes to triplet, first excited state of triplet, it can undergo vibrational relaxation to come to the ground state of vibrational energy level in this particular electronic state, and it comes back to the singlet ground state by a radiative process. So by a radiative process, lambda phosphorescence. Fluorescence is also a radiative process. Radiative processes means upon relaxation, the molecule releases a wavelength of light. Yeah. The fluorescence is in the time scale of 10 to the power minus 3 to 100 seconds. So this portraits the overall electronic excitations and the vibrational relaxation, electronic excitation, and the relaxation of the molecule happening from the excited state through different radiative and non-radiative processes of a molecule. Yeah. If you have any particular doubt about these sort of the time scale or the processes, please raise your queries. If any of you don't have any queries regarding this, we'll only move forward if you don't have any queries. I hope all of you understood what are different processes and what are the time scale of different processes, and which are radiative, which processes are radiative, which processes are non-radiative. I hope all of you understand that. If you haven't understand, please raise your queries, and if you're not completely able to follow whatever I've been discussing so far about the time scales of different radiative and non-radiative processes, please raise your queries. Yeah. If so, I'll move to the second part of the if I'll move towards the second part of the Jablonski diagram or fluorescence explanation of about the emission spectrum. So there is a Stokes shift that happens in the fluorescence emission spectrum. So emission always occurs at a longer wavelength compared to absorption. So we have been asked to explain why fluorescence absorption often occurs at a longer wavelength than exciting radiation. So this is a representative overlay of excitation spectrum, which is denoted in blue, and the emission spectrum, which is denoted in green. And you can see that there is a shift in shift in wavelength maximum, and you can see that the wavelength maximum has increased, right? Compared to lambda excitation and compared to lambda excitation, lambda emission has been shifted to a higher wavelength. So this denotes a Stokes shift. So we have been asked what is the reason behind the Stokes shift of the emission spectrum, emission maximum of a fluorescent molecule. So consider this the one here. Sorry. Consider the one here being the electronic energy levels of the fluorescent molecule. This is the ground electronic energy level. This is the excited electronic energy level. So whatever I had shown in the previous slide, basically these S0 is coming here and S1 is coming here. Okay, and if above all, under every electronic energy level, there are different vibrational energy level that the molecule can populate, and this is the different vibrational energy levels are there in excited states, which also sort of have similar energy gap as that of the ones in the ground state vibrational energy levels. So what happens is, when you excite a molecule, it will go from the lowest vibrational energy level of the ground state to one of the excited state vibrational level. From the excited state vibrational level, so consider this lambda is lambda absorption, and once it reaches at one of the vibrational energy level of the first excited state, it will undergo different radiative and non-radiative pathways, different non-radiative pathways to relax back to the lowest vibrational energy level of first excited state, and from which it will come to the ground state, one of the vibrational level of ground state, using a radiative pathway called fluorescence, where this is called lambda emission, by emitting a wavelength which is called lambda emission. So there is like lot of other non-radiative pathways that have already reduced the energy, that have already released couple of little bit of energy, because of which you will left with only a little bit of energy to, you will left with an energy lower than lambda AB to come back to the ground state. So what happens is, E absorption is always greater than E emission. So we know that E is inversely proportional to lambda. So lambda absorption is lower than lambda emission. So this is something which you can look at the energy level. Sorry, you can look at the energy level diagram to figure out what is happening when there is an excitation. And the main reason behind the emission wavelength being stock shifted is the presence of non-radiative pathways. And the other thing is, so Kasha's rule, which always says that fluorescence only happens from S1 to S0 state, and with V is equal to 0, the lowest vibrational level of the S1 state to the ground state. So because of which yeah, the basis of Kasha's rule is the presence of non-radiative pathways, and it gives rise to a particular rule saying that the fluorescence happens when the fluorescent emission happens when the molecule relaxes from the ground vibrational state of first excited state to the ground state by emitting a wavelength, emitting a electromagnetic radiation. This is just a repetition of the previous slide. Now we have come to the calculation of fluorescence quantum yield. So yeah, so we have been asked to find what is the fluorescence quantum yield. No, so in this question we have been given what fluorescence quantum yield and the fluorescent lifetime of tryptophan in water, and we have been asked to find what is the fluorescence rate constant. So so we know that the class it has been discussed what is quantum yield and how it is being um, denoted. So it can be denoted as quantum yield Q is equal to sorry emissive rate divided by tau plus K in R, or this itself we can call as fluorescence rate constant. KNR is non-radiative and yeah. So the fluorescent lifetime is denoted as can be written as 1 divided by gamma plus K in R. So Q, the fluorescence quantum yield, is equal to gamma divided by gamma into tau, where tau is fluorescence lifetime. So we have to find what is gamma, or the fluorescence rate constant. So fluorescence rate constant, gamma is equal to Q by 2. So Q is 0.20 divided by tau is 2.6 nanoseconds. 1 second. So 1 nanoseconds is 10 to the power minus 9 seconds. So this is 0.20 divided by 2.6 into 10 to the power minus 9. Let's calculate that. This is coming to be 7.6 into 10 to the power minus 2 into 10 to the power minus 9 will come as 10 to the power 9. So this is 7.69. So we can consider it as 7.7 into 10 to the power 7 second inverse. So the fluorescence rate constant of tryptophan in water is 7.7 into 10 to the power 7 seconds. So this calculation is very important because the preceding questions require the understanding of how can we calculate fluorescence rate constant. The radiative, or this also can be called as radiative radiative process rate constant. So how a radiative decay rate can be calculated, or a non-radiative decay rate can be calculated, or how a fluorescence quantum yield is being calculated. So we have to be familiar with these formulas. This one, what is the lifetime, and yeah, things like that. So if you don't understand this particular question, please ask, come on, raise your queries here. I hope since none of you have raised your query, I hope all of you have understood it, and I'm moving forward to the next question. Yeah, so here we have been asked to find radiative lifetime and non-radiative and radiative decays of two fluorophores. So eosin and erythrocin are structurally related fluorophores, and their quantum yields and the excited state lifetimes are mentioned in this particular figure. You can see that. Sorry. You can see that here. So in ethanol, the lifetime of eosin is 3.1 nanoseconds, whereas for erythrocin it is 0.61 nanoseconds, and the quantum yields are 0.665 for eosin, and erythrocin it is 0.12. Now we have been asked to find what is the radiative lifetime of eosin and erythrocin. So one second. Yeah. So tau r is 1 divided by fluorescence lifetime, or radiative lifetime is, sorry, tau r is equal to 1 divided by gamma, and excited state lifetime tau is equal to 1 divided by gamma plus KNR, and we know that quantum yield Q is equal to gamma by gamma plus KNR. So quantum yield can be rewritten as 1 divided by gamma plus KNR divided by 1 divided by gamma. This is same as this one, right? I'm just taking the numerator, I'm just rewriting the equation like this, which says that we can rewrite the quantum yield in terms of radiative and non-radiative lifetime and excited state lifetime. So Q is equal to tau divided by tau r. Okay, so the fluorescence or radiative lifetime tau r can be written as tau by q, where tau is the lifetime and q is the quantum yield. So we know for eosin tau r or tau f fluorescence lifetime is equal to tau by q. So tau for eosin is 3.1 and q is 0.65. So 3.1 divided by 0.65. So it's okay, 1 second. This is in nanoseconds. So this will be 4.76 nanoseconds. For ERB or erythrocin, tau r or tau f is equal to tau by q. Tau was 0.61 and for erythrocin, and the quantum yield is 0.12. So 0.61 nanoseconds divided by 0.12. So 0.61 divided by 0.12 will be 5.08 nanoseconds. Okay, so we have found out what is the radiative lifetime. Now we have to find out what is the radiative or non-radiative rates of eosin and which is gamma and kNr. Okay. Okay. Now, since we know what is tau r or tau f, we can find out gamma from that directly, right? So gamma is going to be 1 divided by tau r or tau f. So tau r here is 4.76 nanoseconds. So 1 divided by 4.76 into 10 to the power minus 9. So this is 0.21 into 10 to the power 9 seconds. Here gamma is equal to gamma or radiative rates or fluorescent rate constant. Yeah. So gamma is equal to 1 by tau r 1 divided by 5.08 into 10 to the power minus 9. So this is equal to 1 divided by 5.08 0.196 into 10 to the power 9 seconds. When 10 to the power minus 9 from the denominator will go to the numerator, it will become 10 to the power plus 9. Okay. Now we have to find out what is the non-radiative rate constants. So for that, first we have to find what is excited state lifetime. So we already know what is excited state lifetime. So how do we do this? So basically you have a tau, which is a function of 1 by gamma plus k n r. This you can write as 1 by gamma tau is equal to gamma plus k n r. So which implies you can write you can write KNR is equal to 1 by tau minus gamma. Okay, so for eosin, KNR is equal to 1 by tau. Tau is the excited state lifetime. So for eosin, that is 3.1 nanoseconds. So 1 divided by 3.1 into 10 to the power 9 minus 9 seconds minus gamma. So that is 0.32 into 10 to the power 9 minus, for eosin it is 0.21, gamma value is 0.21 into 10 to the power 9 seconds. So this is going to be minus 0.112 into 10 to the power 9 seconds. For erythrocin, non-radiative decay rate is equal to 1 divided by tau. So tau is the excited state lifetime, which is 0.61. So that is 1 divided by 0.61 into 10 to the power minus 9 seconds minus gamma is 0.196 into 10 to the power 9 seconds. So 1 divided by 0.61 is 1.63 into 10 to the power 9 minus 0.196 into 10 to the power minus 9, 10 to the power 9. So this is equal to 1.44 into 10 to the power 9 seconds. So the non-radiative decay rate in case of eosin is decay rate is much more lower than non-radiative decay rate of erythrocin. So that's why it has a eosin has a better quantum yield, that you can see from here itself. The quantum yield of eosin is higher than erythrocin because you can see that the non-radiative decay rate of erythrocin is higher compared to the non-radiative decay rate of eosin. So that's why the quantum yield, if you look at the quantum yields, if you look at the quantum yield, this is 0.65 and this is 0.12. That's why erythrocin has a lower quantum yield compared to eosin. Yeah, the second part of the question, assume that the radiative lifetime of phosphorescence. So we had seen what is phosphorescence in a couple of slides back, right? So phosphorescence is the process, it's also a radiative process where the molecule will come from the first excited state of molecule will come from the first excited triplet state at its lowest vibrational energy level to the ground state, and you are assuming that the rate of phosphorescence radiative pathway is same as so we have to assume that the lifetime of phosphorescence lifetime for this both compounds is 10 milliseconds, and non-radiative decay rates are same as the ones that we had seen for fluorescence, and we have to estimate the phosphorescent quantum yield. So one second. This is also same, it follows the same formula, just that we had changed it from fluorescence to phosphorescence. So if you have the rate is equal to 1 by tau p, where tau p is the lifetime of phosphorescence. It follows the same formulas as fluorescence. So this is going to be 1 divided by 10 into 10 to the power minus 3. It's 10 milliseconds, so that's what it is. So this is going to be 10 to the power 2 seconds. So the rate of phosphorescence is 10 to the power 2 second inverse. So for eosin KNR we have found out to be 0.112 into 10 to the power 9. So now you have to find the quantum yield Q. Q is equal to K phosphorescence divided by K phosphorescence plus KNR. So this is 10 square divided by 10 square plus 0.112 into 10 to the power 9 second inverse, which is seconds. Everything is in seconds. So this is going to be 100 divided by, so this is very much more lesser than this particular value, so we can just take this particular value itself, 0.112 into 10 to the power 9 seconds. So this is going to be 100 divided by so this is going to be 8.92 into 10 to the power minus 2, which is 10 to the power 2 into 10 to the power minus 9. This 10 to the power 9 will, when it goes to numerator, it becomes 10 to the power minus 9. So it is 8.92 into 10 to the power minus 7. So you can see that the phosphorescence quantum yield for eosin is very much more less than 1, right? You can see that Q is very much more less than 1. It is nowhere like 0.1, 0.13, things like that. It's way much more less than 1. So that's why we don't see as much of phosphorescence for a lot of fluorescent molecules. So if you calculate, you can calculate for erythrocin. It's going to be the same. So we know that Kp is 10 to the power 2 second inverse, and KNR is equal to 0.11, 1.44. 1.44 into 10 to the power 9 seconds. So your quantum yield Q is equal to Kp divided by Kp plus KNR. So this is equal to 10 square divided by 1.44 into 10 to the power 9 plus 10 square. So we can say that this is approximately equal to 10 square 1.44 into 10 to the power 9. This comes to be 6.9 into 10 to the power into 10 into 10 to the power 9. When it goes to numerator, it becomes 10 to the power minus 9. Sorry, it doesn't have any unit, so it will become 6.9 into 10 to the power minus 8. So which means this is also way much more less than 1. So that's why we don't see any phosphorescence emission for these sort of molecules. Yeah, this is sort of an extended part of the previous question. So it talks about the importance of cash as rule. So when excited to the second excited singlet excited state, as you can see from the previous Jablonski diagram, so we are sort of talking about the excitation of molecule from the singlet ground state here to the singlet excited state, and a second singlet excited state, and we are talking about that process. So yeah, when excited to the second singlet state, fluorophore typically lags to the first singlet state within 10 to the power minus 13 seconds. Using a radiative decay rate constant of eosin in the last problem, estimate the quantum yield for the emission from S2 state. Okay, so this is your S0, S1, S2, and you have vibrational energy levels here. Consider you excited the molecule from here to here. Okay, and there is a non-radiative process which will makes it to come here. So this is the, and we have to calculate what is the quantum yield for this particular process. So this is the radiative process or lambda fluorescence. This is lambda of absorption, and this is a non-radiative process. Now the fluorescence the quantum yield, we all know that the quantum yield Q is equal to K or gamma divided by gamma plus KNR, where gamma is the radiative process, radiative fluorophore. So we have to say that the radiative rate is going to be same as the radiative decay rate that has been found for the found for eosin in the previous problem. So one second, yeah, the radiative decay rate for eosin was 0.21 into 10 to the power 9. So we have to use that here. Right? Yeah. One thing, it should be second inverse. These things. Sorry. This one also should be in second inverse. Sorry about that. All these things should be in second inverse. Yeah. So gamma is equal to 0.21 into 10 to the power 9 second inverse, and your KNR, the non-radiative process, here is going to be 10 to the power minus 13 seconds. Sorry. This is going to be the time scale. So the, yeah, this is going to be the lifetime. So exchange rate is the non-radiative decay rate is 1 divided by the lifetime, which is equal to 1 divided by 10 to the power minus 13 seconds. This is 10 to the power 13 second inverse. So Q is going to be 0.21 into 10 to the power 9 second inverse divided by 0.21 into 10 to the power 9 second inverse plus 10 to the power 13 second inverse. So this is going to be divided by, so we can see that there is a whole lot of difference in the order of magnitude. So we can take this, the denominator as 10 to the power 13 second inverse and numerator like this. So this is going to be 0.21 into 10 to the power 9 minus 13, 10 to the power minus 4. So you can see that the quantum yield for the fluorescence emission happening from second excited state is going to be very less, very much less than 1. Q is very much less than 1. So that's why we don't typically observe the fluorescence emission from the second excited state, and this forms the basis for the Kasha's rule. Okay. So that's all I'm going to explain today about the fluorescence spectroscopy part of the course. Next lecture, next problem solving session, we'll have discussions about FRET and things like that. The FRET quenching, things like that, fluorescence quenching, things like that. If you have any particular questions about the questions that we discussed today, you can raise it now. Otherwise, I'd like to end the session soon. Yeah, sure, Bhagila. I can update. I haven't updated the Excel sheet in the Excel sheet with the links for a couple of, for most of the tutorials, for most of the problem solving sessions. I'll upload it today itself. Okay, I'll upload the PPT as well as the video recording. Okay, thank you.